This is the second lecture from Chapter 18, and it covers voltaic cells, also known as galvanic cells, and that's the type of cell that batteries are. Just as a brief reminder, we're talking about redox reactions. Those are reactions that transfer electrons from one substance to another. And because you're transferring electrons, and hopefully you know that electricity is simply the flow of electrons. So when you have a redox reaction, you can generate electricity. There are two types of cells. There's a voltaic cell. You'll hear it occasionally called a galvanic cell also. And that's different than, I think it's the last topic we'll talk about in this chapter, which is electrolytic cells. Okay. The key difference is a voltaic or galvanic cell is spontaneous. It goes without any outside intervention. And those are the type that provide electrical energy for us. Okay? And that's what we use for batteries. All right. So here's a diagram of a voltaic cell. This diagram is something you want to be able to draw from scratch on your own. And I will tell you as I go through the key things you need to be able to label in a voltaic cell. It's very common for me, for one of my free response questions, to have a big part of a page that's blank and just ask you to construct a voltaic cell and label the various parts. So the first thing is a voltaic cell has two half cells separated. Okay, so you have a half reaction, an oxidation half reaction, and a reduction half reaction that are going on in two separate containers. They are connected with a wire which allows the electrons to flow from one substance to the other. Each half cell contains an electrode. Okay. One of the electrodes is an anode, called an anode, and the other is called a cathode. So the anode gets oxidized, which means the anode loses electrons. Okay, so in this case, with the reaction I've shown here, zinc is the anode. Now it's important if I ask you to label a cell that you don't just put an arrow any old place. Your arrow needs to go to the piece of metal. The metal itself is the anode. So the anode undergoes oxidation, which means it loses electrons, and you can see that here. When you have neutral zinc losing electrons, it becomes the zinc cation. The cathode gains electrons. So the cathode gets reduced. And obviously neutral metal cannot gain electrons. Electrons like to become cations, not anions. So what gets reduced here are the electrolytes in solution. And of course, as copper cation picks up electrons, it regenerates copper metal and plates out on the cathode. There is a salt bridge that connects the two half cells also. And that's because once you start the battery, once you connect everything, the anode starts giving up its electrons. Okay, so the electrons always start from the anode, travel to the cathode. And so what type of charge builds up in the oxidation half cell? Because you're giving away electrons, you have a positive charge that's building up in the anode, in the oxidation half cell. Similarly, a similar line of thought, because you're adding electrons to the reduction half cell, it's building up a negative charge. Okay? So as soon as this reaction has a chance to get going, it's going to stop if it didn't have a salt bridge, because the charge that builds up in the two half cells is not a stable situation. So what scientists have done is they use a salt bridge. What the salt bridge is, it's saturated solutions of a salt. That's a salt that doesn't react, it doesn't interfere with the reaction. And because you're building up positive charge in the oxidation half cell, the anion in the salt bridge will be delivered or attracted to the oxidation half cell. The cation will be attracted to the reduction half cell. So let me give you a whole bunch of memory tricks for remembering all this stuff. I would draw this diagram right now. Okay, here go the memory tricks. Some of the things that you need to remember is that oxidation occurs at the anode, reduction occurs at the cathode, always. So, N-ox, and anode oxidation, chased a red cat, reduction cathode, and ox chased a red cat, okay? So that helps you hopefully remember that oxidation always happens at the anode, reduction always happens at the cathode. Electrons travel from the anode to the cathode. A comes before C. Okay, that's how I remember that one. And finally, when you're talking about the salt bridge, anions are attracted and travel to the anode. Cations in the salt bridge are attracted and travel towards the cathode. So, A goes with A, C goes with C. So those are all my memory tricks. Let's go through a quick review of what's going on the half cell that contains the anode versus the half cell that contains the cathode. The anode is the electrode where oxidation occurs. A positive charge builds up. Anions from the salt bridge are attracted to it. And the anode loses mass. What? Well, let's write what's going on at the anode. So, at the anode, if you go back and look at the image, it showed zinc giving away electrons to form the zinc cation. Okay, so this neutral zinc is zinc metal. That is the anode. And when it gives away electrons, it's no longer zinc metal. It now becomes an ion. And this ion, like most ions, is soluble in water. Okay, so what happens is that solid zinc electrode starts actually losing mass, and you can actually conduct experiments to demonstrate that. All right, moving on to the cathode. That is the half cell where reduction occurs. Negative charge builds up because it's accepting extra electrons, and the cations from the salt bridge are attracted to it to neutralize the negative charge that's building up. The cathode actually gains mass. How is that happening? If you look at the half reaction that's occurring at the cathode in the diagram, we have copper electrolyte ions that are dissolved in water, so I'll just put aqueous. And you have electrons being delivered from the anode. When those two combine, they make copper metal, okay, which plates out on the copper cathode, okay? So the mass of a cathode actually increases over time. I'm going to veer off the main pathway for a moment to just tell you a one-slide piece of information that you'll need. This might be just like a simple multiple choice question. But there is a shorthand notation that scientists use so they don't have to draw a cell every time they want to show somebody what's going on. And here's the basic formula they use. They use a lot of lines. They list the composition or the formula for the electrode first. That's not right. Actually, I meant to change that. For the anode electrode first. Then there's a line, okay, represents a phase change. And then they have the electrolyte solution that's in contact with the anode. This double line stands for a salt bridge. Then they have the electrolyte solution in contact with the cathode. And then the cathode itself. So for this reaction that I just went over, here would be the cell notation for that reaction. Okay, so we have anode, the electrolyte with its concentration, the electrolyte in contact with the cathode, and the cathode itself. All right, so there are two main concepts in this lecture. The first one is what a voltaic or galvanic cell is and diagramming it. The second one is to do some simple calculations about the voltage that is generated by a galvanic cell. That voltage is called the electromotive force, and for short we call it EMF. For even shorter, capital E, okay? So the units for E are V for voltage. So just like you have 9-volt batteries, for example, that tells you the electricity that you can generate from that particular battery. How we do that is we first need to calculate something called a cell potential. And you can see there's a little textbook definition. But every cell has a potential, and it's based on the difference in potential energy between the anode and the cathode. Okay? Each of those has a potential energy, a potential to be oxidized or reduced. And depending on the difference in potentials between those two, that will determine the strength of the battery. So if you hook a voltmeter up, and if you've done the lab this week, you have done that. If you hook a voltmeter up in between the connection between two electrodes, the voltage you get, 0.76 volts, tells you the difference in potential between the two electrodes. The larger the electromotive force, the larger the change in potential energy, the more electrolytic energy you have. So delta E goes up, more energy is provided. We have something called a standard potential, of course, just like we have standard free energy, standard enthalpy. And so anytime, and the reason we have standards is because chemists make up these lists of reference values just so you can compare. You have to have references of things in order to compare values so that you know what's more likely to be reduced, what's more likely to be oxidized. And so, of course, we have standard potentials, E sub cells, that's the electromotive force that's possible from each material. And the standard conditions for electrochemistry are that solutions are 1 molar in concentration. And again, the lab you're going to do this week, you do some under standard conditions, 1 molar concentrations, and others off from standard conditions. So there's a different formula whether you're working under standard conditions or not. So all of the reduction potentials that show up in a reference table are listed as reductions, okay? All of them, regardless of whether they're inclined to be reduced or oxidized. They're all shown in this order, where you start with a cation, or something that's electron deficient, accepting an electron to make something neutral, okay? So this is a reduction half reaction. Again, all of the information in the standard reduction table is written as reduction. And so the materials with the highest value of E, the highest voltage, are going to be most easily reduced. Okay, because they're written in reduction form. How do I know that this is reduction form? Okay, well, reduction means gain electrons. So in any reduction half reaction, the electron is a reactant. If something's gaining something, it's part of the reactant side. Likewise, an oxidation half reaction, which means lose electrons. If you lose electrons, they're given off as a product. They're emitted. So the second reaction is written as an oxidation reaction. What these values are telling you, you have a relatively large positive value for the reduction potential of silver, cation, And that tells you that the silver cation is likely to be reduced. Okay, likely to be reduced. Because when written as a reduction, the E value is positive, okay, which means spontaneous. Okay, so what can we say about if we flip the reduction of silver cation so that it reads as an oxidation? What does this negative 0.8 value tell us? It means that it does not tend to be oxidized, does not want to be oxidized. So if you have a negative value, that implies that that is not spontaneous process, okay? So we can get rid of this. So this is not going to be what silver wants to do. There's not a driving force. It's not spontaneous. And this top one is what silver wants to do. It wants to get erased. I mean, it wants to get reduced. Here's a typical table of standard reduction potentials. Notice that every substance in here has electrons added as part of the reactants. Okay, as I said, they're all written in reducing form. Now, how you can tell whether they actually will get reduced in a reaction or oxidized is by looking at the electromotive force, the voltage. So fluorine getting reduced, adding electrons, there is a positive electromotive force, 2.87 volts. Anything that's positive is spontaneous, okay? It will happen. So fluorine definitely likes to be reduced. So all of these are positive, and they will tend to get reduced until we get to this. And then everything, so here, let me write this, prefers to gain electrons, which means be reduced, right? And everything at the very bottom prefers to lose electrons, okay, and get oxidized. How do I know that? Because when written in reduction form, which is what these are, all of the electromotive forces are negative. Negative values mean non-spontaneous. So if they're non-spontaneous getting reduced, okay, so if it's non-spontaneous in one direction, this is true for any reaction, non-spontaneous in one direction, that means the other direction is spontaneous. So if a reaction as written as a reduction is non-spontaneous, you flip it to be an oxidation, and that will be spontaneous. So you're going to look at these standard reduction tables, and pretty much every textbook has what they call thermodynamic values in one of the appendices in the back of the book. Alternatively, let's see, I think I posted one in the D2L folder for Chapter 18. And you can just Google what is the standard reduction potential, whatever material you're interested in. So here's the formula. But I wouldn't even waste your time memorizing a formula. Let me show you how you do this. Let's say that we want to know what iron does in transforming from iron plus 2 to iron plus 3. As it's written now, which is a reduction, and I know that because the electron is on the reactant side, okay, and also the oxidation number has gotten smaller, more negative. And let's see, the electromotive force or voltage for this reduction of iron is positive. So that means it's spontaneous and it will happen as it is. Now, it's important, you're going to be getting these values out of the table of values, but it's important not to lose sight of some of the trivial things. If you have to, let's say, multiply this half reaction by a digit, in this case 2, in order to maybe equalize electrons transferred on both sides, you do not change the potential, okay? So even though you multiplied everything in the top reaction by 2 to get the bottom reaction, do not change the reduction potential. It stays the same regardless of quantity of material. I have to tell you, I just listened to some of that feedback, and there's that constant roughing and rattling noise in the background. I am so sorry, but I'm too tired to re-record the whole thing, but that noise is driving me crazy. Anyway, I think I had it on a lap desk, so I just took that off. Hopefully that'll help. So how do I get this value? What this reaction tells us is if I put piece of zinc metal and a piece of copper metal together, hook them together with a wire, they would create a voltage of 1.10 volts. How do I know that? We go to the standard reduction table that I gave you about 2 slides ago, and you look up each of these. So if you look up zinc, remember all of them in that table are written as reductions. So if you look up zinc, you get that, and its reduction potential is negative 0.76 volts. And what does this negative tell you? The negative value tells you that zinc does not want to get, or zinc cation does not want to get reduced. It would be much more favorable in the opposite direction. So I'm going to flip this reaction. What was a product is going to become a reactant. And so now, as I've written it now, it is written as an oxidation reaction, where electrons are given off. What you do if you reverse the reaction from the standard reduction table, you also reverse the sign. All right? So that means that, as written here, zinc metal does in fact want to be oxidized, and it is a spontaneous process that will generate voltage of 0.76. We do the same thing with the copper. So look for copper in the standard reduction table, and you will see that copper, different from zinc, actually is spontaneous being reduced. Okay, this E value is 0.34. It's a positive value. Okay, so that's the way it should be written. Then these are each considered a half reaction. You combine the half reactions to give you the balanced electrochemical reaction. That's right here. So what is the takeaway about what to get out of that standard reduction table? Substances that are high up on the table, substances that are high up on the standard reduction table want to be reduced. As you go down the table towards the bottom, those materials want to be oxidized. So if you're trying to pick two substances for a battery, you want them to be as far apart from each other on that table as possible. So let's say you have this arbitrary distance between two substances and it generates X voltage. If you widen the difference in voltage between the two substances, you might have 2x voltage, but you'll definitely have more voltage. Okay, so the farther apart they are on that table, the more electrical energy you'll get from that battery. This is a very typical, straightforward, relatively simple question about voltaic cells. Write the spontaneous cell reaction and calculate E cell, okay, the cell voltage, for the voltaic cell made from the two half reactions below. So what you have to do here, one of the half reactions has to be oxidation and the other has to be reduction. Since they're both pulled directly from the standard reduction table, they're both written as reduction reactions. So you have to decide which one of these to flip and have it become an oxidation reaction. And you select that by choosing the one that will give you the largest overall delta E. And so hopefully you can see intuitively that if I flip the bottom reaction, so instead of being written as a reduction, it is written as an oxidation, okay, that its E value, so anytime you flip a reaction, you change the sign of the standard voltage. So its E value for written this way in terms of an oxidation is plus 2.37. Remember, we want positive values for a strong source of electrical energy. And so now we know the bottom one is going to become our oxidation half cell, which means we leave the top one as it is. And we have to find the, add those together. Once we have the correct signs, you simply add them together. And so the total voltage of this cell is 2.52 volts. This was not a really very hard lecture, was it? I'm trying hard to put a little bit less material in one lecture. Maybe I can hold your attention a bit more. And so now what you need to do, you know how to balance electrochemical reactions. Now what you need to do is a bunch of practice problems for determining which half reaction is going to be oxidation, which is reduction, how to use the standard potentials to generate overall cell potential. So there is a worksheet in the in-class problem-solving folder, and I would recommend pulling that out and getting some practice.